Hello, this is Bernie Zeigler. I'm going to talk about how theory and abstraction drive progress in simulation science and practice. This was a keynote talk at the Summer Simulation Conference in 2017. In outline, we'll consider that abstraction and its concrete realization are essential for progress in knowledge, and we'll see how important they were in particular cases that I think will make the case that this is a very important way that knowledge develops, and especially in modeling and simulation. Where abstractions enable uncluttered thought, concrete realizations of them are closer to reality. They are necessarily messy. So progress can be considered as a certain progression from abstraction to formalization to implementation in reality, exemplified by the work of George Boole and Alan Turing. But in modeling and simulation in particular, abstractions lead to new model representations which drive the development of new computational environments. In particular, we'll see that DEVS, a discrete event system specification, was an abstraction that was formalized using set theory and system theory, and drove the progress from programming languages to modeling and simulation computational environments supported by high-performance information technology. This talk will emphasize that progress continues with deeper theory and new abstractions. We'll talk about iterative system specifications as more comprehensive and deeper representations that include DEVS and that are aimed toward dealing with broader problems that go beyond particular disciplines but require multidisciplines or even better combinations of new disciplines to include old ones from a multi-perspective point of view. And we'll look at examples from healthcare to aviation and cyber systems. So let's consider the progression from abstraction to formalization and implementation. Abstraction, according to the dictionary, is the drawing out of a general quality or characteristic apart from its concrete realities and specific objects or actual instances. So it's an idea, a very nice idea, that focuses on some aspect of reality and pulls it away from all kinds of messy details and complications, and just allows us to focus on some particular concept. But such an abstraction is just lies there as a nice idea until it can be turned into something real, and that requires that it be formalized, put into a formal framework, where that means to develop and state rules in symbolic form in some way, such as logic or mathematical form, from which inferences can be drawn, and concrete development of these implications can be made, so that eventually the idea leads to what could be called a reduction to concrete form or implementation. But that necessarily introduces the messy context of real world and to some extent complicates the abstraction, and eventually may stimulate the production of more comprehensive abstraction or better abstractions. And this cycle of from abstraction to formalization, implementation, can continue in a spiral, hopefully increasingly more productive manner. So examples that I think will make the case that this is a very important progression I now will discuss. One is a Boolean algebra, which is an abstraction of logic in natural language. And we can identify that with the book by George Boole in 1854, An Investigation of the Laws of Thought, on which are founded mathematical theories of logic and probabilities. This can be thought to have started with informal reasoning, or how we make the arguments in natural language about beliefs that we want others to adopt, and goes back to the Greeks, if not earlier, and a form that's familiar to logicians, propositional logic. But we can identify the Boolean algebra as the first real formalization, and that reduced the propositional logic to symbols 0 and 1, and operators that allowed to compute or manipulate these zeros and ones into combinations that then could be assigned values of 0 or 1. And this led to Boolean logic or circuits for computing. And but the important point was this was still an abstraction until it could be actually implemented, and that meant it had to be implemented with actual electrical signals, such as voltages or currents, and the quantization, or the breaking down of a signal into parts. Some part below a threshold might be assigned to 0, and above a threshold might be assigned to 1, and that way the logical circuits could be implemented so that they came out of the existing circuits for electrical signals. That led to the concepts and implementations of transistors and the tremendous explosion of microelectronic chips that enabled manipulation of millions and millions of zeros and ones to represent states and computations, and the answers that could be obtained with very, very fast and very powerful computers. Now, an allied abstraction was the Turing machine that Alan Turing invented about 100 years later, and that comes out of the notion of informal effective computation and what it means to compute something or use an algorithm. It was a sequence of steps to carry out to get to a result, and but it hadn't been formalized until Turing put down in more concrete form, but still abstract, this concept of a control with finite number of states, working on a tape that held symbols, and that could then be shown to be as powerful as any computation could be, or computer could be produced in reality. But the road to getting such an abstraction into actual practice went through recursive function theory, which was being developed around that time by mathematicians and logicians, and in particular a form called lambda calculus that was one of the contenders for the theory of recursive functions, and that led to an implementation of an artificial intelligence language called Lisp, which then led to the tremendous radiation in programming languages and software systems that we all know about now, and that drive all the control and underlie the web and the internet and all the good and bad things that are coming about with that kind of underlying technology. Interestingly, the notion that such programming systems are getting too complex and it's very difficult to interoperate or take somebody's programming developments and combine them with somebody else's. It recently was pointed out in a paper that said perhaps we should return to the Turing machine as a basic concept and see if that leads to more uniform development. But that was also questionable. So let's look at this progression from abstraction to formalization and implementation in the case of modeling and simulation. There's a very interesting paper by Hollux on the dawn of simulation, focusing on the contribution of K.D. Talker in intelligence, innovation, and integrity. And Talker was dealing with the early modeling in the 50s and 60s of steel plants in England, and that they all had a certain similarity, of course, of steel production, but varied also tremendously in their different technologies, equipment, and layouts in their different locations. And Talker had to conceive a framework that would address the steel plant problem more generically. But it's interesting that the core idea or abstraction that we're talking about came to him somewhat like a eureka moment while in a bath, and he had the concept of a system consisting of individual components, which he termed machines, and progressing as time unfolded through states that changed only at discrete events. So he perhaps was the first to abstract the concept of states and events underlying the new programming languages that were being developed to model these steel plants and other industrial facilities and communication networks and early computers that were being developed at that time. And this led to more of a formalization in terms of a three-phase process, which, first of all, you could consider his the complexities of steel plants, which had many processes, many components, and many interactions that could be conceived as going around in cycles and interacting with each other. Talker abstracted this three-phase structure led by events, where some events were scheduled and some events were contingent on the occurrence of other events. And time progressed not in steps, but through the occurrence of events and the timing of events. This, as part of this progression, we can take the development of devs and see it in this framework. From the early computerized simulations of the 40s and 50s and 60s, which were manifested in event-based simulation, the abstraction occurred was discrete events and states that Talker had conceptualized, and then the formalization in terms of devs to discrete event system specification and the family of models that it engenders, and the implementation through the dev simulator and the devs simulation systems that allow the simulator to compute the consequences of the devs models and produce results that could be of interest to modelers. So in this regard, K.D. Talker could be credited with the first concept of state and event-based abstraction. It described but was not a formal foundation for simulation. And then devs formalized this abstraction, and it became the foundation for a family of simulation systems. Now, what is devs? A little overview. It stands for Discrete Event System Specification, based on Weimar's system theory. It distinguishes between structure and behavior and has a hierarchy of specifications, where at the lowest level we can conceive of a black box where we know the interface of the box, but all we can see is inputs and outputs over time, and make correlations between the inputs and the outputs. And the concept of atomic uncoupled models was inherent in the Weimar system and formalized in the devs framework, by which you could construct complex systems, first atomic, put those together to get coupled systems. And then the concept of closure and decoupling, that the resultant of coupling of well-defined components is also well-defined devs, and that led to the ability to construct models in a hierarchical fashion, putting components together, get bigger ones, and putting these together with others to keep creating more and more complex systems. And that's a hierarchical model, modular composition, and supports complex system development. Also, the devs allows the structure of the model to change while it's running, so that we can get meaningful changes in the underlying rules of behavior. And this is very important for new concepts that are being developed for how complexity can emerge from simple systems, simple components that are put together and become more and more increasingly complex, and their structure can change. Devs has a history of development outlined here, and a few examples of milestones. The history beginning in 1976 or so with classic devs defined, and various developments and extensions are listed and shown here on this timeline. I won't go into detail, but there has been a considerable development, and a fairly large research community has emerged. An overview of some of these milestones are given in a recent paper, which you might want to refer to. But the focus of this talk is on a second spiral of revolution that I referred to earlier, where the first abstraction leads to developments that get more complex and attempt to solve more difficult problems, and this leads to new abstractions intended to strengthen the original one and make it more capable. So in Dev's case, we could say the original abstract problems were traditional operations research kind of problems. Now we're addressing a more expanded range of problems that we'll talk about in a moment. That leads to more expanded abstraction, where in addition to system states and events, we'll add the concept of input and output segment generators. And I'll describe that in a moment, which leads to a more expanded concept of Dev's formalization, and that will be called iterative system specification, and that will hopefully then lead to an expanded tool set, an expanded range of capabilities of Dev space modeling and simulation environments. This expanded range of problems, put in the context of a term that's starting to be used called convergent science, which is illustrated here with in the context of computational frameworks as conceived by Mamadou Traoré, which conceives of computational frameworks as based on platforms with supporting environments that provide tools, techniques, languages, and theories and methodologies and concepts for particular kinds of computational frameworks. And they have their applications in different disciplines. And traditionally, the disciplines have been very isolated from each other, more or less. The real problems, though, require more than one discipline, many disciplines, and that has been called multidisciplinary. But as Andreas Toth pointed out, beyond that, somehow these disciplines have to interact with each other, which leads to interdisciplinary conceptions, and more than that, you may need new disciplines developing that are more broad and more capable, and may combine different disciplines and new transcending level of discipline. This is exemplified in a framework along the computational framework point of view by Powell and Mustafi, which points out the need for a hybrid modeling and simulation study, which is the use of different methodologies from different disciplines within the same study, within the same development. And one of its basics is that it will be useful to have the generic frameworks for modeling and simulation, such as DEVS and UML, to support these concepts where you're not tied down to one particular discipline. And this would support the co-simulation of both different kinds of model types, such as discrete and continuous, and also the same time deterministic and stochastic models, and maybe other kinds of model types, all in the same framework. Now, the iterative system specification aims to make systems concepts effectively computable and more capable of supporting this transdisciplinary, multi-perspective, hybrid capabilities that are being conceived as necessary to deal with the expanded range of problems. Now, the idea of the iterative system specification is that it combines effective computation theory, which we've seen, for example, in the Turing machine, which has finite states and a transition function, which is a single operator, and introduces the notion of iteration and recursion and computation and also the limits in computation, which is exemplified in the halting problem for the Turing machine. When does, under what conditions does a algorithm halt and give a result? Now that is distinct from Weimar's system theory, which not only includes finite states, but continuous time-based and continuous states, and a global transition mapping that is over a period of time, how states evolve over such a time period. And that's distinct from the central abstraction in computation theory and computer science, which conceives of states as evolving one after the other in sequence, but not necessarily in time. And so we can't really conceive of states happening in relation to each other through time, whether when they are close together or far apart, or other before and after relationships in time. And that is one of the central distinguishing features between computation or computer science and modeling and simulation, that has a broader view and incorporates structure and behavior in a well-defined system, and a composition that allows systems to be composed together to create bigger systems. The result of this kind of combining of effective computation theory and Weimar systems theory is a way to specify systems in an event-like manner that is exemplified by DEVS, but transcends it, more capable, and allows us to deal with a broader range of problems. Well, to discuss iterative system specification, we'll focus on the Turing machine itself for illustration. It's an example of unitary design or non-modular design, but it is decomposable into simple components, and then to compose them together to get back the original system with simple coupling. And in a sense, it's a good example of emergence, because each of the components, the tape and the control machine, are pretty dumb by themselves. They can't do very much, but when coupled together, they create the maximally smart system, that is one that can, in principle, do anything, any computation that can be done. And this will illustrate the basic concepts of iterative system specification. So here's a Turing machine picture taken off the web, where somebody has actually constructed a physical realization, and it has a tape and reading symbols 0 and 1, and a head that reads the tape and can move it left, right, or stay in the same position, and a control that has states, a finite set, and can make decisions based on reading the tape and what state it's in, to move the tape left to right and write some symbol on it. And this can be represented by components, the tape with its tape state, which is a sequence of zeros and ones, which can be extended indefinitely, and an input and output port, where a symbol and a move can come in and change the position to the move state, and write a symbol on the tape, and the current symbol at the current position can be read and output. So the other component is the Turing machine control, which has a state and which can produce this pair of symbol and move, and also receive a symbol from the tape. Now, in devs and in the underlying system theory, these components can be coupled together. Each is an open system that having input ports and output ports that match nicely in this case. And we add coupling, which takes the output of one and feeds it to the input of the other. And then we get in this case, a well-defined system, which is the resultant coupled model. Here's a view of Dev's model of this Turing machine, the components, the control, and the tape system, and then the coupling specified by the coupled model. Now, so far Dev specified a well-defined closed system, but what if the tape elements are not discrete symbols, but have continuous durations and profiles as they would in reality? And what if such a symbol comes in to the control component while it's still processing the previous symbol? What happens then? These kinds of timing issues and non-crisp versions of symbols can't be immediately stated in devs, although they can be eventually represented. But what helps to do that is to address these kinds of questions is iterative system specification. And here we see that the idea for iterative system specification, as discussed before, is that we're combining the systems concepts of Wymore system theory with the effective computation concepts of recursive function theory and Turing machines to get a more extended version of DEVs. Actually, eventually that will be itself simulated by DEVs. But these kind of specifications put back what was abstracted away to get events of the kind that are represented by the original Turing machine. The discrete states and the symbols, and it allows us to put back much more of what was left out originally. So the heart of iterative specification is to describe how a system responds to input generators, that is, finite intervals of time segments. For example, here we have a constant that lasts a certain period, like up to time t, and that would be a class of such generators if we let t be any finite number. So that gives us a set or class of generators, and we could have a set or class of generators where the constant is, say, a value that represents null, that is, nothing is happening. Because if we want to say that an event is happening or something's happening, we have to have something that represents nothing. And, well, 0 does that when we're talking about the real numbers. But if we're talking generally, we need something that's another symbol like a null. And a third set of generators here is a continuous pulse, but lasts over some time less than some time t, for example, less than 1. And this is a class because this pulse could be very, very narrow or wider, depending on what t is, and it's a certain set of such pulses. So we have 3 types of generators here, and they can be composed by concatenation, so that one follows another, and we put a finite number of those together. So here we have a null generator lasting till t1. Here we have a constant generator lasting till t2. And here we have a pulse lasting from t1 plus t2 to t1 plus t2 plus t. And then finally we have a null generated at the end. But we need to have a way to parse such finite segments into their generator components, into the sub-segments. So, for example, here we would have them parsed into a null lasting t1, a constant lasting t2, pulse lasting t, and a null lasting t3. And this can be done with maximal length segmentation, which extracts the longest successive generators. And of course, you'd want to have the longest one because if you had any shorter ones, then you would have more than one to represent a situation where you could do it with just one. And so we want to get the smallest number of generators coming out. and the biggest intervals or durations that can be characterized by a single generator. This requires distinguishability of the generators when concatenated, and remember that we encounter systems in the real world where we might say we want to break down their input segments into generators where we're not given at the beginning. We don't impose how the generators are put together, but we have to parse or have to figure out, or the system representation has to know when generators are operating, which ones at which times. Now, we can compute with these generators in the sense we have a system, we know its initial state, and we have an input segment made up of generators, and we also need to have for each generator and each initial state, the state that the generator takes us to at the end of its duration. We get a big jump from the initial state to the final state, and then we take that final state as initial state for the next generator, and we get a next jump like that, and then this continues on. In this way we compute the state trajectory, and likewise, once we have the state trajectory, we can also compute the output trajectory. So what we get is the input-output behavior, the input-output function for each state. What this does, it gives us a very efficient way of computing a system. Instead of doing small steps that would otherwise be necessary, such as discrete time steps, we take one big step and represent all the effects of the small time steps. That might mean we have to pre-compile knowing the small time steps, or it might be that we do an analysis to represent the overall transition. But once we have compiled into this overall large step size, large step state transition, we have an efficient way of computing the system's input-output behavior, which in fact is what we want to do. That is what effectively computing the system behavior is all about. So now we know how to compute the system given its generators and their transition functions. But when is the resulting assemblage system? Well, for atomic component systems, or atomic systems, we compute the I/O function as we have just described, and we've gone through these steps 1, 2, 3, and collecting the input-output pairs into an I/O function for each state. But now we also want to talk about how to put these atomic component systems together in a composition. And just as in devs, we have a means by which we define a composition of systems. And here we have to go a little further into depth, because we have now the I/O function for each component for a given state. Let's say we're given the starting states. But here we have to guess what the input generators are, because the outputs go back through the coupling into the inputs, and we don't know those either. So We could compute the outputs given the inputs, but we don't know what the inputs are because they may depend on other inputs coming from other components. Actually, you could say we have to guess. Take a guess of what the input-output pairs are for these starting states, and we have to keep searching until we can find a consistent input-output assignment. When we do that, we can then advance time using the MLS maximal length breakpoint, the shortest one, because each output segment will have one, and then we take the shortest one, and that's where time advances to, and then we have to go and compute, go through this cycle again, and we do that until the time period that we're interested in has been reached, has been consumed. Well, that leaves us with a problem because we have to satisfy these requirements, but we don't know in advance whether they can be satisfied or what it means to be satisfied in some overall sense. So now we're going to define what a well-defined system means. When does an iterative specification define a system? Well, let's see what the situation looks like after we have discussed this composition of components. Remember that the state of a composition is more like a vector than a single state. So each component is in a state, and if we collect them together, put them in a list, we have a more like a vector, and the state transitions for the system now are these transitions in this vector space. But we can imagine that each vector now is represented by a state in the abstract sense, like here in terms of a single symbol. And that this represents the state of our knowledge when we compute the resultant system. So, for example, if we start in state 1, it could be that the system might go to state 2, but we also know how much time it will take, because remember, that maximal length segmentation will take us until the next break in time. We do know the time transitions for transitions that do occur, but we still have problems. So let's see. The system may not be defined at some state, say S8, because there's no trajectory emerging from it. So here's S8. And when we get there, we're stuck because there's no satisfaction of the requirements there for inputs to match outputs and so on. The system is non-deterministic at S1 because there are two distinct outbound transitions defined for it. And it's deterministic at S2 and S4 because at S2 there is an outbound transition which takes infinite time, or that's okay. That means we stay there. We go to S2, back to S2, and S4 because there's only one outbound transition for it. What we want is that all states are deterministic, that they all are defined and have a single outbound transition. because at this point we're looking for deterministic result. We want to put these components together and be able to say something definite about what happens. So we say that the system is well defined if it's deterministic at each state. But also we have to worry about something else now that's a consequence of the fact that we're talking about time here. Here we can see that time has to advance as we go from state to state. And here we get into a situation down here where time doesn't advance, where we get into a cycle, and so time doesn't move forward, and we can't say for some later time what the state is. It seems to oscillate all the way from S4 to S5, S6, S7. We don't know what time it is. So we say that a trajectory is progressive in time if time always advances as we extend the trajectory. So if we can extend the trajectory and time keeps advancing, we say that that trajectory is progressive, and we would say that the system is well defined if it's deterministic and progressive at each state. So each trajectory coming out of that state is progressive, and we can always say with certainty after a certain time what state, given any time, what state the system will be in. That would be something we certainly want to do. Now, this generalizes the concept of legitimacy for devs. Devs has the same kind of requirement. We know that the situation does not have to be getting into a finite cycle of zero transition states. It could be one where we have that the times accumulate to some finite time, and that's where the system sort of hangs up. And that's what's been called the Zeno-ness property after Zeno, the Zeno paradox with the hare and the turtle, where they progress half distance to a goal each time and never get there. And this is a similar situation.